Next up is Ramadi Hagazda. He's a PhD, founder of Cognitave. His previous industry experience was a senior RF engineer at S12 Technologies. He has over a decade of experience in computational simulation and modeling, fabrication, and testing of RF and microwave devices and systems. It's application questions for electronic design, automation at Keysight Technology, or for the ODEs. He's led pioneer research academic over 5 years and on novel nano composite based pre-configured site material applications in electrically scanned phased array at Raytheon UMass Lowell Research Institute. He is recipient of 2 U.S. patents, 2 awards in R&D. He has published peer-reviewed articles in the Journal of Applied Physics and IEEE microwave theories and technology. He's a U.S. citizen and computer digital screen technology integration. He's been in Boston, also does online presentations for us. Like I mentioned earlier in the conference, the IEEE has 40 different technical societies. So some of the folks in Seattle in my group have RF, so I'm trying to connect the dots. So with that, please come. Madi.
Yes.
What's your last name?
Hagzadeh.
Go ahead. Got it working?
Yes.
Thank you. Welcome.
Thanks very much.
Yeah.
Thanks. Good afternoon. Thanks for your attention. My name is Mahdi Hagzadeh. I'm founder at Cognitave Inc. Cognitave Inc. is a technology and innovation-based company founded in 2008, and it focuses right now on 2 areas. One is advanced algorithms for, say, radar signal processing, or some other application we are considering at the moment. And the other area is developing software to design electronics without paying high amounts of money for licenses. Of course, it is in the area of RF microwave and electronics engineering. So my talk has 2 sections. One is more on the application side and software to design electronics. On the right side, the latest advanced mathematical development and R&D. So I will give a brief summary of work we've done in radar for advanced vehicular system. And this is a software environment, and we've used neural networks to speed up one of the main algorithms that are behind the working on the radar, called direction finding or music multiple classification algorithm. The second part is our approach is to use open source software and be able to integrate them and input algorithms that will speed up processing, simulation, and modeling. On the right side, you're going to see a lot of equations and some results based on a couple of software available online. So, looking at autonomous driving, it could be for automotive, could be for drone, could be for any number. There's a number of sensors, and you get a lot of data. You have to use them. There's a lot of algorithms running on them. Of course, lots of power, lots of cost. So it has been towards chipsets that are AI friendly. Some of them are specifically made to be low power. Neuromorphic computing is the latest chipsets that bring mimic brain and processing and memory are co-located. We don't need to push the data between processor and memory. These are very advanced architecture here. So they are not one human. So there's non-one human. They're not traditional. There are a number of companies have been working, and now they're in market. There are platforms that they take advantage of all the traditional architecture and new architecture. So it's pretty much state of the art. So we are looking at this model here. So it's modeling 3 cars, and this is the radar signal. So this one is the Eagle car, has the radar, and then this is in a simulated environment in software made by Matlab. And these are real radar signals running some algorithms, FMCW. It gets to this point, maps the distance and speed and so on and so forth. And behind this, you get the data, you convert them to the digital data, and you have megabytes and gigabytes of data. You sort them out in this queue, and you do FFT, fast Fourier transform. You shuffle the data around, and then you do a search algorithm where you pick up the strongest signal, and you know something's there, and you keep track of it, and you avoid noise and clutter, and you get a graph like this. So it shows the 2 objects here. This is working out commercial as well as military radars, and the chain of signal processing, and all these backed by some mathematical algorithms and equations. So in this part, what we did, we used a neural network to take care of the main prediction planning algorithm. Instead of solving the equation mathematically, it trains over a range of data and becomes a lookup table very fast. However, this was in software environment. Applying it to real data from the street might be a challenge. Previously, we've shown that by making a model work, we look at how the whole model works with the neural network-based algorithm, and we've shown that in this model environment, we solve the problem with the equation 30 times fast. And if this goes on some special chipset, that might be even fast. So this is the area that we are pretty much focused on in terms of application, so radar for vehicular system. In this section, we are looking at how do you do this? How do you design algorithm? How do you model working on radar? And in general, there's CAD-based computer-aided design software, the portfolio, I mean, a big list of them. But in general, to make chipsets or to make electronics, PCB boards, we use this sort of computer-aided design for electronic design automation. For chipset, this is a process. For radar, you would design, you simulate and model it, you will send it to fabrication and test it. But this is pretty much the design flow for that application. Some of the softwares that are industry standard are Matlab from Keysight, which used to be Agilent, and before that was Hewlett Packard. So these are very expensive units. Some of them cost 20 million for hundreds of users across the DoD industry. And then we are focused on open source. Open source means there's a big community of scientists and engineers. They work on similar software, and it's free. And you can use series of them to get to work. And so we focus on this sort of applications. First of all, because the startup self-funded so far. Okay, I'm listing a number of them. But what is the importance of mentioning them. Behind all of these, there are the equations, mathematical equations, and you numerically solve them to know how the device is going to work. So at this point, I'm going to switch to the second section where we are introducing a new algorithm that is not implemented in any of these tools so far. So this is based on a number of publications that I've known for years from my master's in Sharif University of Technology in Tehran, Iran. So it has a very innovative way of looking at the RF microwave problems. And here's the equations I will go quickly. So we have an equation here, it's second order. This is a solution. It makes a matrix out of this part, and this is a solution for one interface. So these come from quantum mechanics and optoelectronics, where you have a wave propagated in an environment where the properties of that environment change from one layer to the other. When you look at one interface, solve the equation for one, and they jump to the second, to the third, and then in the limit when you take an integral of that, it becomes a general formula. So there's a number of applications that back up this report, this method, and it's called Differential Transfer Matrix method. So here we have a full article on it that lists all the equations. Then you bring it into an environment like Matlab or Octave, which is the free version of that software. This is how the code looks like. After writing a couple hundred lines, you give an equation and we are solving it versus a standard algorithms in these environments. So red one is our algorithm, and that one is blue one is the standard method to solve any differential equation. So at this point, we are trying to be general, give any equation. The problem with solving equations, if it's any arbitrary equation, some of the algorithms solve, some of them take much longer, some algorithms cannot even solve it. So our approach is basically test the algorithm in various ways. So we are looking at some very difficult equations, and we can see that it can solve them with very good accuracy. Of course, if you want more accuracy, it will take much longer time. And so we are looking at some different methods here, because how you input these equations varies in how they will perform. Again, so we are looking at different software, Mathematica. This is more of a symbolic, different way of looking at the problems. But again, we here show that our method works in the environment too. We coded it, we executed it. It comes close. These are very difficult equations, but it is able to solve. And then in a number of different configurations that we are testing those. And sometimes you have a singularity. At some point, a signal just disappears because you have 1 over 0 and it goes to infinity. But the algorithm has some tricks that you can solve that problem. So you might, for let's say a pedestrian in front of a radar, just at some angle with guardrails on the side, you might miss that first because the algorithm, because of how little that information is, could go out of control. But this is robust in that case. And then different configurations, some approximate methods, again, all linked to the algorithm, and publications exist that they have solved this sort of configurations of that equation. Again, another one we implement in a different variation, and all of them we test the time it takes But it is difficult to know how fast this algorithm is versus the other one. So they're using a PC or a Mac, and how much of processing it will take, that will give to the seconds and fraction of seconds that takes for this algorithm to use the memory and process it and get to the solution. So numerical approach. What is it? Where is it? Yeah, so that's imaginary. So imaginary of so it's a complex. We're dealing with complex numbers. So it's a complex equation. It has imaginary and real part. So articles claim that it is faster and more efficient way of solving these problems. So we have an approach, and a little bit more work needs to be done to actually prove that. But it's more exact. It's an analytical solution. It's not a guess of the result. It's actually mathematically complete. We look at the variation of these equation under this method, differential transfer matrix method. But the point is, once we complete this algorithm, we will write a code to go in one of these open source software, and that will be our edge in solving some difficult problems and advanced signal processing. Even though AI has a lot of promise, when it is on the edge, it doesn't have access to server, we don't have training. Having a complete solution to the problem that is ongoing. A radar on a drone is flying, or you have a very light IoT type radar sensing. They don't have access to even battery over time. This is where these sort of algorithms will come handy. They'll be faster, will consume less power, and more accurate. So a number of references. I mentioned some of them are from my professors at my master's program. Thanks so much.
Any questions from the audience? So I had a question. So where do you see this industry 3 to 5 years from now, and the type of jobs students like yourself just completed, but what do you say to new students? Is this an industry that AI won't touch, or?
AI is taking everything by storm. However, I'm saying mathematics are not going away. AI is mathematics, but engineering is there. This is analytical. It's a complete solution. It's no guesswork. I'm more focused on that sort of problem. I mean, mathematics is a difficult topic, and AI takes a lot of attention from all the students and new generation. Yeah. You're going to miss on that part because everyone is going to just plug in and use models, but what is behind models? For 10, 15 years I'm working with software. If you don't know the root cause of working out of these models, I don't think you can go far. Another trend is the softwares that I showed. Companies have access to some license-based software. These cost companies hundreds of millions of dollars over span of 10, 20 years. Okay. So my company's approach is we will use open source and we will save millions of dollars for those companies if they put the time and resources to build their own simulation and modeling software. That's our approach. The business model is there's open source code that we can invest money and engineers' time to perfect them and configure them with other open source. So you own your own software. You don't need to license it.
I'll ask the next obvious question. If you're doing all open source, how do you guys get paid? Who's your client? You take grants?
Well, we get paid by configuring it. by training it, but because let's say a specific company has a license, they have application engineers.
Right.
So we'll have application engineers expert in those.
So you actually train their
Yeah,
engineers.
so they don't pay for the license, but to maintain it, to advance it.
So if there's issues, the help desk, they call you, they charge you,
Yes.
or you charge them up.
Yeah, we'll work with experts that, expert consultants that they've been working with these software for over years, and they can address any issues.
And then I guess the next question is it a lucrative industry to get into, or
Yes.
is it just a
It's like I mentioned in DoD, a number of companies I know each pay tens of millions because they have thousands of engineers who use the same software. I should know the number. It's very lucrative.
okay? So, and you're a citizen,
Yes, I am. Yes.
Any last questions? All right, thanks for coming.
Thanks very much.
Appreciate it. Okay, so up next we got special guest.